Welcome to 15.6, which is all about surface area. This is basically our last of the big applications in our unit on double integrals. So the real question is, if I have some surface S, and I'm going to say here that the surface S, in this case, is a function. It's z as a function of f of x and y. We'll actually find out later in the year how to do surface area of things that aren't functions. But z equals f of x, y. Can we find the surface area of this? Now, you did this in BC Calculus for a couple special circumstances, surfaces of rotation and things like that. But we want to be able to do it in general. So what we're going to do is we're going to ask this question. For some surface, right, if I cut out a little section delta A at the bottom, right, rather than trying to find the volume or anything else like that, the question is, can I figure out what the little bit of surface area is in the section that corresponds to that? If I go up and just cut out a little section of the surface, can I figure out how much surface area is in that? And if I can, then I can kind of do my double integral and add it all up. Now, it turns out that that's a little challenging to do. So what we're going to do, as we so often do in calculus, is we're going to approximate. So rather than trying to find that little bit of surface area directly, what we're going to say is, what if we just assume that it's, more or less flat on the top? We're going to assume that that little bit of surface area is actually equal to the area of the tangent plane. We're going to make a tiny little tangent plane approximation. Happy little tangent plane right there. So we're basically going to create a little tangent plane right at that little spot and approximate it that way. And I've kind of given you a zoomed in drawing right here. Here's our little delta A, which is of course still delta x, delta y. And here is our little unit of area, delta t. Now, if I take this little tile, and again, it's going to be tilted a little bit, right? Because it's going to be a tangent plane as close as I can get it to whatever the surface is at that point. What I could do is if I can define two vectors, A and B, that represent the sides of this little flat thing, then I have, fortunately, a tool that gives me the area swept out by two vectors. This is just the magnitude of A cross B. So if I can find those vectors, I'm going to be okay. Turns out that these vectors are not too difficult to find. For starters, if I look at A, it extends a distance delta x in the x direction. So delta x I hat. It doesn't have any component in y, in this case. And if I want to know its z component, well, it turns out that one way I can write this is I can write this as the x derivative times delta x. How do I know that that's the case? Well, think about kind of what a derivative means, right? If I zoom back to just simple little BC stuff, if I want to make a linear approximation somewhere, right? I've got a delta x, and if I want to know, delta y, or in this case delta z, it's just rise over run. It's going to be slope times delta x, which in this case is, dy dx times delta x. I know that's really tiny and difficult to see, but I'm basically just justifying that this is rise over run times, well, the run. And by the same token, my vector b here, I can write as delta y j hat plus fy delta y k hat. So let's go ahead and take our, switch colors here, and we'll take our cross product. So we're looking for A cross B, and then we'll go ahead and find the magnitude of that. So I'm going to give myself lots of room. I hat, j hat, k hat. Been a little while since we did a cross product. We've got delta x, 0, f of x times delta x. And here we've got 0 delta y, fy delta y. So if we take this cross product, we end up with I hat times nothing minus fx delta x delta y minus j hat. This gives us fy delta x delta y plus k hat delta x delta y. So what we end up with is, notice how there's a delta x delta y everywhere. What we end up with is this vector, negative fx, negative xy1 times delta a. And that does mean, if we're trying to take the magnitude of this, that what we end up with for that magnitude, that little area segment, is the square root of fx squared plus fy squared plus 1 times delta a. And in this case, what that means is that if I want to find my surface area, I just need to add those up. And we actually usually just restate this in a slightly different way. We usually write it as the square root of, we usually put the 1 first, dA. And this is, I just want to note, over the region R, which is going to be, once again, the shadow of that in the xy plane. Wow, my pen is going to run out here. There we go. So the surface area of S is given by the double integral over this region below. You'll notice a couple things. One, this kind of looks like what we have already. This kind of looks a little bit like our arc length, right? It's sort of reminiscent of our arc length equation that we had before. Okay, so we're going to do an example of this in just a moment. I do want to take a quick aside, though, and address something right now that is the cause of some confusion sometimes later. So I want to actually look at this vector here. This vector, negative fx, negative fy, comma 1. This vector comes up actually kind of a lot. And there's a secret to this vector. And the secret to this vector, actually, maybe you can figure out the secret to this vector. Notice we got this by doing A cross B. So this is a vector that should be perpendicular to both A and B. That is, this vector should be perpendicular to the surface at every single point. It turns out that this is a version of a gradient. This is a version of the gradient vector. How do we arrive at something that doesn't really look much like the gradient vector? It sort of does, but it's got some negatives and it's got a 1. Well, remember that we're considering here functions of the form z equals f of x, y. But what if I rewrite this a little bit instead and think of it not as z is a function of x and y, but what if I think of this instead as, what if I think of this instead as a function of 3 variables, z minus f of x, y. And I want the specific level surface of that function where z minus f of x, y equals 0. And hopefully you can kind of see that this and this are the same. I just subtracted f of x, y away. Well, if I look at the gradient of g, I end up with, well, taking my x derivative, z doesn't depend on x. So I get negative fx, z doesn't depend on y, 1. Because the derivative of z with respect to z is 1. So this is not something you need to like memorize or whatever. However, we're going to see this vector pop up a couple more times in future units. And it's just important to know that this is a version of the gradient vector that will give you a vector perpendicular to your 3D surface. So don't worry too much about that. Let's return to our regularly scheduled program, and we'll do a little example. So our example here is we want to find the surface area of the paraboloid z equals x squared plus y squared below z equals 9. So let's just quickly sketch that, because again, if you're doing a double integral and you're not sketching it, you're doing something wrong. So here's our paraboloid. And notice we're cutting it off here at the top at z equals 9. It's worth noting that that means that this corresponds to a region. It's got a circular shadow on the xy plane of radius 3, in that case, of radius 3. So what we can do here is we can take some derivatives. We can look for zx, which is 2x, and zy, which is 2y. So we can find our surface area here by doing the double integral of 1 plus 4x squared plus 4y squared dA. Now, we probably want to do this in polar because we're doing it over this disk. This is, again, the shadow in the xy plane. So we're just going to change our integral up a little bit. It's going to be r, there's our extra r for polar, 1 plus 4r squared dr d theta, r from 0 to 3, theta from 0 to 2 pi. Now in this case, I'm going to need to do a little u substitution. Or I guess I don't need to, but I want to. 4r squared du is 8r dr. So I'm going to end up with a 1/8. I also want to note that my theta integral, there's no dependence on theta. So the whole purpose of my theta integral is just going to be to multiply by 2 pi. And then we end up with root u du. And our bounds, if I plug in 0, I get 1. And if I plug in 3, I actually get 37. So it's now the integral from 1 to 37 of root u du. This gives us pi over 4 times 2/3 u to the 3 halves from 1 to 37. And so I'm running out of space, I'll do it over here. We end up with, these cancel, and we end up with pi over 6 times 37 to the 3 halves minus 1. And there's our final answer for this example. Note, you often end up with these kind of weird, because there's a square root in the formula for surface area, you often end up with kind of weird looking answers. All right, in any case, this is the main formula you need to do surface area, so good luck, and we'll do some more examples in class.